We've already looked at alkene addition reactions, but to this point we've not described them with any mechanistic considerations. Alright, so an addition reaction is what is formally known as an electrophilic addition reaction. And an electrophile is an atom, molecule, or ion that seeks negative charge, so it's essentially the opposite of a nucleophile. Alright, so we're going to have a look at ethene. So ethene is CH2, CH2. There's a double bond between the two carbons. Alright, and each of the carbons is sp2 hybridized, as you can see here. And each of those sp2 hybrid orbitals will form a sigma bond. Alright, so there will be one of the bonds between the carbons is a sigma bond, and then each carbon makes two sigma bonds to the hydrogens with using the hydrogen 1s orbitals. This leaves on each of the carbons an unhybridized p orbital, so for sake of argument we'll call it the pz orbital. Right? Because these orbitals are parallel to one another on adjacent carbon atoms, this results in what's known as a pi bond. Okay, remember back to pi symmetry. Right? A pi bond is formed both above and below the plane of a sigma bond. So, and it's formed at parallel p orbitals on adjacent carbon atoms. Now the pi bond is electron rich, so that means it's quite attractive to an electrophile. Also, due to the nature of the pi bond not being axial overlap, but being this parallel orbital overlap, it's weaker and therefore is more susceptible to reaction. So a very electron-rich center that is naturally weaker than a sigma bond is a great site for a potential reaction. So let's represent ethene here, and then we'll take something simple like bromine, molecular bromine. Bromine has no naturally occurring dipole, but if Br2 gets close enough to the double bond, the electron-rich pi bond, what happens is a dipole becomes induced, meaning that the electron density temporarily shifts to one of the two bromine atoms, alright, making one partially positive and one partially negative. The electrons from the double bond are allowed to attack the partially positive bromine, while the bromine-bromine bond electrons are transferred to the partially negative bromine. This results in a temporary carbocation, okay, that is then reattacked by the bromide ion. The resulting compound that's formed is 1,2-dibromoethane. Okay, so we have successfully added Br2 to an ethene molecule. Now what happens if we take what's known as an unsymmetrical small molecule, and we'll add that across an unsymmetrical double bond. So we'll consider propene, as shown here, and we're going to add HBr to this. HBr is naturally polar, right? The hydrogen-bromine bond is partially positive, partially negative, so we don't even need to induce a dipole. The electron-rich alkene will attack the partially positive hydrogen, and the HBr electrons will be transferred formally to bromine, making bromide. So now we have two possibilities of where could that hydrogen go from the HBr. I'm just going to keep the colors consistent here. So I can say that the hydrogen from HBr would add to the second carbon in the carbon chain there, which would make a carbocation forming at the first carbon, and then this would leave free bromide, which would then readily attack the carbocation, forming 1-bromopropane. The second possibility would be the hydrogen would add to the first carbon in the carbon chain, okay, forming a carbocation at the second carbon, which would then be attacked by the bromide ion, which will result in 2-bromopropane. Now, from experiment, we know only one of these two molecules will actually form. So in order to consider which one it is, it's best to examine the actual carbocation intermediate. So the first option we had what's known as a primary carbocation. The second one will find a secondary carbocation. From our work with the SN1 reaction, we know that a primary carbocation is highly unlikely, and a secondary carbocation is far more likely. Not as preferred as a tertiary, but of the two options here, the secondary is far more likely to stabilize the positive charge. This is the only product formed, and this is what is known as Markovnikov addition. The carbon with the most hydrogens will always receive the hydrogen. The more highly substituted carbon will receive the heteroatom, in this case bromine.